Hello everyone, hope everyone is doing well. Today we're going to learn about confidence intervals, and we are going to learn what it is and how do we measure it, or how do we find it or calculate it. Now there are different methods of calculating confidence intervals based on whether we know certain information or not. So as a result, this video will be broken down into 3 different parts. So this is part 1 of measuring confidence interval. Now let's think about what is confidence interval. Now in a previous lecture, we talked about the central limit theorem. And in that theorem, we basically said that if we have, let's say, a known, or let's say we don't know the population mean and the population standard deviation. So in that case, if we were to repeat our experiment, our sampling over and over again, then the average of the sample means will basically be closer and closer to the population mean. So this is just in short, I have a lecture about this, like how we can see that the sample means form, like repeated sample means taken together, they look like a normal distribution. But this is just a very, very short, watered down version of the central limit theorem, which we will need right now. However, one of the problems here is that it relies on, if I want to find the population mean, it relies on me taking multiple samples and then finding the sample means of each of them. But in that case, it gets a little difficult for us to do that. The reason is, well, it does get very expensive, not just time-wise, but also monetary-wise, to take a survey, and repeating a survey over and over again to get closer and closer to the population mean gets even more difficult. So, and in many cases, we just have one shot to find. So we just have this one shot or one opportunity, quoting Eminem, that this is what we have, and we have to get our inference about the population mean from this sample mean. So let's say we took a sample. Let's say my sample 1 has n of 40, and I find that my x bar, which is my sample average or sample mean, is 55, and my s bar, which is my sample standard deviation, is 4. Now from here, this is what we would call a point estimate, because it's giving me the idea about just one point that we have. From here, we have to then make an inference about what is the population mean, which we call mu, and the population standard deviation, which is we call sigma. So mu is my population mean, and sigma is my population standard deviation. So what we do from here is, basically, since this is just a point estimate, if I'm thinking about what my sample is, so 55 is a number, and I'm saying this is the x bar. Now, from here, I have to figure out, okay, what is the population mean? The chances that the x bar I get, the chance that x bar equals mu, the population mean, this is very, very low. So we probably, just taking one small sample of n equals 40, we will probably not get the actual population mean. But what we can do is that we can find some kind of an interval or a range around this sample mean. And this number then gives us a starting point, and we can say that, okay, yeah, I understand this is the sample mean, but this gives me some information, and it can tell me that maybe the population mean is somewhere between these two intervals. So the lower limit and the upper limit. So we can say that based on this, based on the sample mean, that is x bar equals 55, I can find a range where I could infer that based on this mean, the standard or the population mean is going to be within this range. And this range is called confidence interval. So this confidence interval then tells us that based on what we get as our sample mean, if let's say my lower limit is going to be a certain number, x, and or since it's x bar, let's use another name, let's say a, and the upper limit is b. So I could say that the sample mean is 55, and based on that, I am this much confident, or the confidence interval at this percent is going to be between A and B. So mu could be here, it could be here, it could be exactly 55, we just don't know where, but we put a bound that it's going to be probably between. Now, how do we find confidence interval? So there are three ways we actually could find confidence interval. Now, so one way could be, and it is one way, is that one method of finding a confidence interval is if the population standard deviation is known to us, but the population mean is not known to us. The other one is, one method would be if supposing we know the population standard deviation, then we can use one method to find the confidence interval. The other one is that the sigma, the population standard deviation, is also unknown. So we are going to use these two methods, supposing that sigma is known and supposing sigma is unknown, to find out how to find my confidence interval. Now let's look at an example. Okay, what we are doing here is, let's say we are using our original value. Let's say we have, this is the x bar we found, which is 55. And I want to find what is mu, just reiterating it. And I want to put a band around it to make sure that the population mean is somewhere between these two numbers. Now, the level of confidence that we choose, so we choose 3 levels of confidence. So some people like to be 90% confident. Some people like to be 95% confident. And some people like to be 99% confident. We are never 100% confident. 100% would basically mean that, yes, the SX bar is 55, and it basically ranges. The population mean is somewhere between negative infinity and positive infinity. I could say that, and I would be 100% confident of that, but that really does not give me any information. So let's start with, we can pick one of these later, but let's look at this now. So we have to pick these two numbers, and we have to find out these two numbers. Now what we can do is, and we learned about this before, is that we can use something called a z-value, which we calculated before, and z-value was x bar minus mu divided by, let's say we know the confidence interval right now, and let's say we know the value of our standard deviation, so sigma over square root of n. This is coming from central limit theorem, let's say. So I can calculate my z-value, so I can transform each of these numbers using the z-value, and I could convert this into a standard normal distribution, where now my x bar becomes 0. And then these bounds are now at z-values. So using the z-value, I basically converted my regular distribution, which is a normal distribution, into a standard normal distribution. Okay, so now what we are saying here is that, okay, so let's say mu was 55 in my case. So then every possible range of x bar has been looked into, and so this is what it is. Now let's say I want to pick a level of confidence at 95%. So if my level of confidence is 95%, it means that I want to be 95% confident that the population mean would be in between this range. and 5% that it's outside of this range. Now 5% cannot be on one side and 0% on the other side, so what we do is we write 2.5% is in one end and 2.5% is in the other end. So in that case, I can now go back to Excel to find out what my z's are. So if my z is 2.5%, I can do norm.inv, norm.s.inv, since I have it at standard normal distribution. So divided by 2, 0.05 divided by 2, this gives me negative 1.995 or negative 1.959. So plus minus negative 1.59 or 1.96. So then I can say that this lower bound is negative 1.96 and this upper bound is positive 1.96. So if this is my range, now if I want to find where is mu in this whole thing, so mu, if let's say the mu was somewhere, let's say very close to the sample mean, let's say it was at 53, then the population mean would be right here. But if the population mean is way outside, then it would be out here. But we want to be 95% confident, so we will be within this two range. So then all the numbers within here are possible candidates. The extreme is going to be negative 1.96 and positive 1.96. So then I can say that the z values, the extremes are, so again, I'm just writing x bar minus mu divided by sigma over square root of n. So then the extreme value would be, or the limits would be, I'm just rounding it up to 1.96 equals x bar minus mu divided by sigma over square root of n. So this is in the denominator. If I multiply both sides by sigma over square root of n, so I can write sigma over square root of n times 1.96 equals x minus mu, or x bar minus mu divided by sigma over square root of n times sigma over square root of, then these two get cancelled, so we're done with these two. And so what I get is x bar minus mu. And now if I rearrange, if I add, basically if I make this a negative, then this is a negative, then this becomes a positive. I'm just multiplying both sides by that. And then I can say that this implies that my mu equals x bar plus, or minus here, 1.96 times sigma over square root of n. Now, this is if it was positive. Now, this is one side, so the other side would be negative, so we can put a plus minus here. Then this would become a plus minus, then this would become plus minus, so our formula then becomes plus minus. And this gives us our confidence interval estimate. So writing it in a nicer form, we can say that, so this becomes our formula for confidence interval estimate. So now let's look at the case where population sigma, or population standard deviation, is known. So supposing we're using our same example above, so let's say my x bar is 55, and I know that the s bar, or the sigma, let's say s bar is 5, but I know from maybe a previous experiment or something that the sigma is 6 and my n is 40. So if this is my number, then I have to find what is calculate the, let's say we want to find the 95% confidence interval of the population mean given those numbers. So I know my x bar is 55. Now this part that we have, this is what we call a margin of error. So let's find first, let me bring this here and I will delete this. So first we have to find z alpha over 2, which we actually did first here, so we don't need to do that again. So the margin of error is going to be equals to 1.96 times the sigma is going to be 6 here, divided by square root of 40. So we get the number, this number. So this is going to be, again, we're writing margin of error. So we found this number. Now, if I go back to my diagram again, I found out that if this is going to be my normal distribution that I have, where the sample mean is 55, then the margin of error is telling me that I go 1.86 to the left and 1.86 to the right. So, and these ends are now the 95% confident intervals. So basically then, if I need to find those numbers, the lower limit is equals to 55 minus the margin of error, which is going to be 53.14, and the upper limit is to be 55 plus the margin of error, which is 56.85. So this lower limit will be 53.14, and the upper limit will be 56.86. So then I can say if my sample mean is 55, then based on a 95% confidence interval, the population mean could be anywhere between 53.14 and 56.86. So reiterating that. So then if the sample mean is 55, the 95% confidence interval is between those two numbers. Now, what if I wanted to find, instead of 95% confidence interval, what if I wanted to find the 90% confidence interval? So let's say I want to find, so if I were to find the 90%, this won't work, but I can use the same formula here. So what I will do is, instead of writing the 0.05 over 2, 90% means that the midpoint is going to be, if I go back to my graph here, that means that this middle point will be 90%. And what's left over then is on the two sides, then we have 10% left over. So then instead of being 2%, 2.5 and 2.5 on each side, if I have 10% left over, it will be 5% to the left and 5% will be left over to the right. So with that, I would then go here and I would just write z.norm.s going to be 0.1 divided by 2, and we get 1.644. So then we do the same thing. We have to first find the margin of error. So I can just write here, margin of error now will be equals to 1.644854. If you notice, I'm just dropping the negative sign because it's plus minus, so I don't need the negative sign right now. Then my sigma is going to be 6 divided by square root of n is square root of 40. And so my margin of error is this number. So then my lower limit will be equals to 55 minus the margin of error, and the upper limit 55 plus the margin of error. And this will give me the 90% confidence interval. So if the sample mean is, so if you notice, the 90% confidence interval is a little smaller than the 95% confidence interval. Now if I were to find the 99% confidence interval, I would do basically, instead of this number, I would write, so let's say calculate the, so 99% would be, since I have 1% left over and I have to divide it across the two sides, so it should be that number. So then my margin of error, and so the lower limit and upper limit would be 55. So my lower limit would be 52.55. My upper limit would be 57.44. So I am 95% confidence. I am 99% confident that the population So now I'm 99% confident that the population mean is between these two. So we have just done our first part, which is if the population standard deviation is known. If I know the population standard deviation, which is here, which is sigma, I will use the normal distribution to find my z-values. So in this case, all that we have been doing so far, so I'll just reiterate that. So if I have that known, then I will use z-values to find my confidence interval, and I will use the normal distribution to find the z-values. So basically, in this case, whenever we look at the margin of error, the formula here, we have z-values here. If the population standard deviation is known, we are going to use this. Now, in the next part, in part 2, we are going to see that if the population standard deviation is unknown, and for the most part, it is probably going to be unknown because, if we don't know the mean, how are we supposed to know the standard deviation? In that case, we have to use a different technique. It's similar, but slightly different. We have to just update what our z-values. Okay, hope this was helpful, and I'll see you at a later lecture. Goodbye.